Welcome back to Lesson 3 on quantitative aspects of chemical change. In this lesson, we will look more into the mole and volume calculations. So, to calculate mole from volume, we need this equation. Mole is volume of the sample divided by the molar volume of the substance. This equation can only be used at STP if you want to use the Vm as 22.4 cubic decimeters. Okay, you can still use the equation, but not 22.4 if the situation is not at standard temperature and pressure. Or we could use PVs in RT, the ideal gas equation. So we're going to look at some examples now. The first example, I want to know what is the volume of 2.3 moles of hydrogen gas at STP. So you could use any of the two equations above. So I'm going to, just for the sake of using both, I'm going to do the example that way. The mole is the volume over the molar volume. So the mole is 2.3. At STP, the molar volume is 22.4. Please don't guess this value, it is on the data sheet. And we want to calculate the volume of the hydrogen gas. So it is 22.4 times 2.3, which is 51.52 cubic decimeters. We could take the other path, PV equals nRT, where the pressure is standard pressure, so it is 101.3, yes, kilopascals, but in this equation it should be in pascals, times the volume. It is 2.3 moles, and the universal constant is 8.314, and the standard temperature is 273 Kelvin. So if we use this, the volume would be 2.3 times 8.314 times 273 divided by 101.3 exp 3, and that gives us 0.05153, and this would be in cubic meters. So this is 51.53 cubic decimeters. You must be able to convert from cubic meters to cubic decimeters, and from cubic decimeters into cubic meters. So we multiply by 1,000, or we divide by 1,000, or 10 to the power 3 if you want to do that way. Example 2 says hydrogen reacts with chlorine to form hydrogen chloride. Write a balanced equation for this reaction. So hydrogen is a diatomic gas, chlorine is a diatomic gas, and it forms hydrogen chloride, which is a gas, and to balance the equation, 2 of it. Write down the mole ratio, B. So the mole ratio is 1 mole hydrogen to 1 mole chlorine to 2 moles of hydrogen chloride. C. Calculate the number of moles if 11.2 cubic decimeter hydrogen chloride is formed. So C wants the number of moles if 11.2 cubic decimeters is formed at STP. So it is 11.2 divided by 22.4, and that looks like 0.5 mole of hydrogen chloride formed. D. Calculate the volumes of hydrogen and chlorine that reacted during this reaction. So the mole ratio is 1 mole hydrogen to 1 mole chlorine to 2 moles of hydrogen chloride. So if you've got 0.5 mole, then 0.25 mole of chlorine and 0.25 mole, so 0.5 mole will have half that chlorine needed, 0.25 mole, and half that hydrogen chloride. Hydrogen is 0.5 mole. But I don't need to take this route because the mole ratio and the volume ratio is exactly the same. So the 11.2 cubic decimeters of hydrogen chloride will require half of that, which is 5.6 cubic decimeters of chlorine, and 5.6 cubic decimeters of hydrogen will be required, because the mole ratio and the volume ratio deduced from Avogadro's law will be exactly the same. Example 3. A balloon contains 4 grams of oxygen at STP. Calculate the volume of the oxygen. So number A, the mole equals volume divided by molar volume. But I don't have the moles, I have the grams. So to get moles, it's the grams, the mass, divided by the molar mass of oxygen. So it's 4 divided by 2 times 16, which is 0.25 mole. Let me just check myself. 4 divided by 32 is 0.125 moles. Yes. So 0.125 equals volume over 22.4. So the volume would be 2.8 cubic decimeters. Number B, the number of oxygen molecules in the balloon. So the number of particles would be the moles times Avogadro's number. So the moles is 0.125 and Avogadro's number is 6.022 times 10 to the 23. So 0.125 times 6.022 exponent 23, and I get 6.77 times 10 to the 22 molecules. Last question, number of oxygen atoms in the balloon. So for one molecule, you have 2 atoms. So the number of atoms would be double the number of molecules. Now I kept my answer on the calculator, so my answer here will be different from yours. I didn't round it off, so times this by 2 is 1.355, 10 to the power 23 atoms. Right, next example 4. What volume of oxygen at STP is needed for the complete combustion of propane? So the mole ratio is 1 mole propane to 5 moles oxygen to 3 moles carbon dioxide and 4 moles water. So the mole ratio and the volume ratio is exactly the same. So if they say 3.3 cubic decimeters of propane, then it's 5 times 3.3 cubic decimeters of oxygen. So the volume of oxygen is 5 times 3.3, which is 16.5 cubic decimeters. Right, example 5, they have ammonium nitrate is explosive used in the mining construction industry. During the explosion, nitrogen, water vapor and oxygen is released. Determine the total volume of gas formed at STP if 2 moles of ammonium nitrate is used. So the mole ratio is 2 to 2 to 1 to 4. And the volume ratio would be exactly the same. So the volume, I don't need to do that. I can say that STP, the total moles of gas, is 2 plus 1 plus 4, that is 7 moles of gas would form. So the volume of 7 moles of gas at STP will be the moles times the molar volume. So it's 7 times 22.4 cubic decimeters, which is 156.8 cubic decimeters. If you wanted to do them separately, the volume of the nitrogen would be 2 times 22.4, and the volume of oxygen would be 22.4, and the volume of water would be 4 times 22.4. So I think if you go take this route, then you'll get the same answer. So that's 44.8 cubic decimeters, and this one is double that. That's 89.6 cubic decimeters, and if you add them up, you'll get 156.8 cubic decimeters. So 2 ways to do that. Right, my time's running out on this. Try this one by yourself. The airbags in vehicles are activated during a collision by an electric spark that ignites the sodium azide, and 40 milliseconds. This is 40 times 10 to the minus 3 seconds. Just use that. Right, try this one. Enjoy.